The magnetic field shown in the figure given below is directed into the plane of the paper. ACDA is a semicircular conducting loop of radius r with the center at O. The loop is now made to rotate clockwise with a constant angular velocity omega about a point passing through O and perpendicular to the plane of the paper. The resistance of the loop is R. Obtain an expression for the magnitude of the induced current in the loop and plot the graph between the induced current and omega t for the period of 2 rotation. So in this particular problem, if we analyze this case, so initially when the semicircular conducting loop is outside the magnetic field, there is no flux change associated with it. Now as this loop will be introduced in the region of magnetic field, so some flux will be induced in it and an EMF will be induced. So let us look at this at an instant when the thing is rotated by an angle theta. So I am drawing another big diagram for our understanding. So this is the region of magnetic field which we have, and I am considering that this semicircular loop is rotated like this, and on being rotated, this is the new patch that is introduced into it. This is the new patch that is introduced in the region of the magnetic field. So I am considering that this angle theta and this one is a new area that is being introduced, so I am calling it as d theta. So this is the flux change that is taking place right now, this area. And if the radius is equal to r, so I can take that this length is equal to r d theta, and hence the area associated with this can be written as dA, as we are considering it to be a small triangle, so half base into height. So we write it in this sense. So the value which we obtain is equal to r square d theta by 2. So this is the change in area which is taking place at this instant of time as it is rotated, and it must be kept in mind that d theta by dt will be written as omega, which is equal to angular velocity for the system. So if the magnetic field is B, so I can say that therefore the EMF induced is equal to B into A. So B into A is r square d theta by 2 by dt. So the change in flux by time taken is what we have done. So d phi by dt. So the flux is equal to B into dA, and then we have written it as B into dA by dt. So we calculate the value of EMF induced, which is equal to B omega r square by 2. So the value is coming out to be B omega r square by 2. So this is the value of EMF induced in this frame. Now what more must be kept in mind is, so as this loop is introduced into this region, so now what is going to happen over here is, so in the first case, as the loop is getting introduced, so the magnetic field associated with this loop is increasing, so the current will be induced in the anti-clockwise sense. The induced current is such that it opposes the cause producing it, so it is in anti-clockwise sense, and we treat anti-clockwise current as a positive. So over here, if I calculate the value of current induced, so I can write that the induced value of current or the current induced can be written as EMF upon resistance of R. So it will become B omega R square by 2, and the resistance of the loop is capital R. So okay. So one thing must be kept in mind, this one is small r. So we are making this as small r for the time being. I am making the resistance as small r and the radius as capital R. So we have solved the considerable length. So we can write the current induced is equal to B omega R square by 2 small r. So we have taken this radius as capital R and resistance as small r. So this is the current induced when the loop is getting introduced into this region of magnetic field. And now the next part which we say is, after the entire loop is introduced in the region of magnetic field, that is if I draw a system like this. So after half the rotation, so this is going to be the loop. So it will be completely into the magnetic field and it will be moving out of the magnetic field. So when this loop will be moving out of the magnetic field, so now what will happen? The current will be induced in the clockwise sense. And if the current is introduced in the clockwise sense, so we consider it as negative. So if I draw a graph between the induced current and the value of omega t, so we can say it in this way, that if we mark the notable point, so the graph is going to be in this way, that when it is rotating by value pi, the value is positive. For the another pi, that is till 2 pi, the value is negative. For another pi, the value is positive, and then for another pi, the value will change again. So for the first half, the value is positive. For the another cycle, when the loop is moving out of the magnetic field, the value is negative. Again for the other half, the value is positive, and again the value will be negative. So I can mark this as B omega by 2r, and this one as B omega by 2r. So this is going to be our variation of current with time that is going to take place for this particular problem. Figure given below shows a circular coil of n turns and radius a connected to a battery of EMF E through a rheostat. The rheostat has a total length L and a resistance capital R. The resistance of the coil is small r. A small circular loop of radius a dash and resistance r dash is placed coaxially with the coil. The center of the loop is at a distance x from the center of the coil. In the beginning, the sliding contact of the rheostat is at the left end and then it moves towards the right at a constant speed v. Find the EMF induced in the small circular loop at the instant the contact begins to slide, and in the B part it has slid through the half the length of the rheostat. So if we consider this problem, we consider in this way. I am drawing it in an enlarged way. So over here we are having a circular loop like this, which will be carrying a certain current, and the current will be a function of time. It is because of the fact that the rheostat's resistance is continuously changing. So as a result of this current carrying coil, which is having n turns and radius equal to a magnetic field will be produced at a distance x. A magnetic field will be produced at a distance x, which is the center of this smaller coil which we have. So this smaller coil is having a radius a dash. So the magnetic field at a distance x can be written in this way: B is equal to mu naught Ni a square upon twice of x square plus a square to the power 3 by 2. So this is the value of magnetic field due to this current carrying circular coil at a distance x, and hence the flux through the small coil can be written as mu naught Ni a square upon twice of x square plus a square to the power 3 by 2 times of pi a dash square. So we have multiplied it with this area, and over here we can calculate that the rate of change of flux is regarded as the magnitude of EMF. So if we calculate from here the magnitude of EMF, which is equal to d phi by dt, so we can write it in this way: mu naught n pi a square into a dash square upon twice of x square plus a square to the power 3 by 2 times of di by dt. So we wish to calculate this rate of change of current over here now. So apart from this parameter, we are left with the finding of this value of the rate of change of current. So we are considering it in this way, that the x length of the rheostat will offer a resistance which will be equal to Rx upon L. The L length of the rheostat is offering a resistance equal to R. So the X length of the rheostat will offer this resistance, and hence the current through the battery can be written as I is equal to E upon the resistance offered by this X length, that is Rx upon L, and the resistance of the coil, which is equal to small r. So from here, if we calculate the value of di by dt, so di by dt can be written in this way, that we can take El as constant, sorry, and we can differentiate this part Rx plus Rl with respect to time dt. So if we solve this expression, we get di by dt is equal to El, and if we differentiate this expression, we can differentiate it in this way: Rx plus XL whole square, and we will get a minus of derivative of this entire function, that is derivative of Rx plus Rl with respect to dt. So from here we obtain a value equal to El, this will be R, and dx by dt can be written as V. So the term dx by dt is written as V, and the derivative of RL with respect to dt will become 0. because it is constant, and we are left with this expression Rx plus XL whole square with a negative sign. So since we are writing di by dt magnitude, so we are omitting the negative sign for the time being. So this is the value of di by dt which we have. So if we put this expression in the value which we have calculated previously, that is this expression of EMF induced, so we will get the value of EMF induced as a function of x. So if we do so, we obtain the EMF induced value as, so EMF induced can be written as mu naught n pi a square a dash square upon twice of x square plus a square to the power 3 by 2 times of ERLV upon Rx plus RL whole square. Now the question is asking us to calculate the value over here at 2 instant when the contact began to slide and when it has slid through this half the distance or half the length of the rheostat. So over here we can do a simple thing. Now for the A part, the value will be when x is equal to L. So if we put x is equal to L over here in this expression, we will obtain the value of EMF induced in the A part, which we are calling it as EA. So it will become mu naught n pi a square a dash square ERLV upon twice of x square plus a square to the power 3 by 2. And if we put L over here, we can take L square common, R plus R whole square, and we can remove this L from here. So on cancellation, we obtain this value that the EMF induced in this part is equal to mu naught n pi a square a dash square ERV upon twice of x square plus a square to the power 3 by 2 into L times of R plus R whole square. So similarly in the B part, what we have to do is we have to put x is equal to L by 2. So if we put x equal to L by 2 in the above expression, we can obtain the answer easily. So I am leaving it that part for you. So this is how we solve the value of EMF induced for this particular problem. A wire AB of length L, mass M and resistance R slides on a smooth, thick pair of metallic rails joined at the bottom as shown in the figure given below. The plane of the rails makes an angle theta with the horizontal. A vertical magnetic field B exists in the region. If the wire slides on the rail at a constant speed V, then we have to show that the magnetic field value B is equal to root over mgr sine theta upon VL square cos square theta. So if we are considering this particular problem, so we are considering that the particle or the rails is moving down or sliding with a velocity v. So if it is sliding with a velocity v, then the current is induced in this direction in this conductor and in this rail like this. So this is the direction of current that is induced in this segment. Now if we calculate or first of all find the direction of magnetic force, so I say that the magnetic force is acting in the upward direction, that is F magnetic will act in this direction. This is determined using left hand rule. So over here I can say that the first thing which we calculate is the EMF induced. So EMF induced can be written as BLV. Now when we write BLV, it is important that BL and V are perpendicular to each other. So for this particular aspect, when the motion is in this way, so we are understanding this from the side view. So if I draw the side view of this arrangement, so this is the current carrying wire which I am representing by only one end of it. Then the weight component which is acting in the downward direction is equal to mg sine theta, and the magnetic force is acting up the incline which is equal to Fm. So the velocity component which is perpendicular to the magnetic field will be this. So this is the value of velocity which we have. So the velocity component perpendicular will be v cos theta, and the length component will be L cos theta. So the value of EMF induced can be written as B L cos theta into V cos theta. So the value is going to be BLV cos square theta. So this is going to be the EMF induced. So the value of current which we calculate in this particular circuit is equal to EMF induced upon resistance, which is equal to BLV cos square theta upon R. So this is the value of current which we have, and hence the magnetic force F magnetic can be written as BLV, sorry, and hence the magnetic force can be written as ILB, and it is equal to B square L square V cos square theta upon R. And now if this metallic rod is to move with a constant speed v, so it is important that the net force on this must be 0. So hence I can say that F magnetic is balanced by mg sine theta. So if it is balanced by mg sine theta, so from here I can calculate the value of magnetic field. So the value of magnetic field will turn out to be B, which is equal to mgr sine theta upon V L square cos square theta and square root of this entire term. So we have proved this expression. So let us move to the next problem. So the next problem is stating a rectangular wire frame shown in the figure given below has a width d, mass m, resistance r and a large length. A uniform magnetic field B exists to the left of the frame. A constant force F starts pushing the frame into the magnetic field at t equals 0. Find the acceleration of the frame when its speed has increased to v. Show that after some time the frame will move with a constant velocity till the whole frame enters into the magnetic field. Find this velocity v0. And the last part is asking show that the velocity at the time t is given by v equals v0 1 minus e to the power minus ft upon m v0. So this is the expression which is to be proved. So if we start understanding this problem, so the first thing which I wish to state over here is the following facts. So as this loop enters this region of magnetic field, so the force that is being applied is equal to F in this direction. So as it is will be inserted into this magnetic field, a current is induced in this loop in this direction. And the cause of EMF will be because of this length segment. So we are understanding by drawing a circuit equivalent to this in this fashion, such that the entire rectangular loop is offering a resistance R. So these two arrangements will help us in understanding every bit of this particular problem. So the EMF induced formula is BLV, which we have learnt, and the direction of current will be in this way as we have already seen. So now due to this the first set of calculation which we need to do is this: the width is d in this case, so I write that the EMF induced will be equal to B dV. So it will be B dV, and because of this the current that is going to flow in this segment is going to be B dV upon R, where R is the resistance which is given to us. Now due to this, a magnetic force will act on this rectangular loop. So this force, magnetic force which will act on this length of the wire, can be calculated as ILB, and the value of ILB will be obtained as B square D square V upon R. So the magnetic force is calculated as B square D square V upon R. Now the direction of magnetic force can be calculated using Fleming's left hand rule, and if we consider this for this wire, so the direction of current is this: the magnetic field is directed into the plane of paper, and the magnetic force is calculated or observed in this direction. So the magnetic force is opposing the value of applied force, and hence I can say that the net force which is going to act on this rectangular frame can be written in this way, that F net is equal to F minus F magnetic, and we can write it as F minus B square D square V upon R, and this will produce an acceleration which we are calculating by equating it to ma. So from here the value of acceleration can be calculated as Rf minus B square D square V upon mr. So this is the value of acceleration which we have for this particular problem. Now if we look at the problem is stating find the acceleration of the frame when its speed has increased to v. So this is the first part which we have calculated. Now in the next aspect it is asking that show that after some time the frame will move with a constant velocity till the whole frame enters into the magnetic field. Find this velocity v naught. So now as the entire loop enters the region of magnetic field, the force which is acting on the loop will become zero, and the net force will be zero as the force will cease to act. So now if it will cease to act, so it will move with a constant velocity. So if velocity is constant, I can say that acceleration is zero, or we can directly equate the equation of force. So from here I get F is equal to B square D square V upon R, and the maximum value of velocity which can be attained, which is equal to V naught, is equal to Fr upon B square D square. So this is the value of V naught which we attain, Fr upon B square D square. Now in the next problem it is asking to find the velocity as a function of time, or to prove that it will be of this kind, that v equals v naught 1 minus e to the power minus ft upon m v naught. So in order to begin this approach, we begin by solving this equation. So I can say that acceleration a can be written as dv by dt, and we can equate it with rf minus b square d square v upon mr. So from here we write dv upon rf minus b square d square v is equal to dt upon mr. So now we integrate both sides. So at t equal to 0, the velocity was 0, and after a time t, when the entire loop is entering the magnetic field, we say that the velocity is v. So from here I can write that velocity at any instant of time can be calculated in this way. So if we integrate this, we will obtain ln of rf minus b square d square v upon minus b square d square, where the upper and lower limit is 0 and v, which is equal to t upon mr. So if we substitute the value, we will obtain this expression as ln of rf minus b square d square v minus of minus plus ln of rf So over here we have minus of b square d square, and this one is positive b square d square is equal to t upon mr. So over here we can rearrange this term, and the expression is going to look like this: v is equal to rf upon b square d square 1 minus e to the power minus b square d square upon mrt. So this entire thing is in power e to the power. So this is the expression which we are going to get. So from here I can say that this expression is equal to v naught. So this is the equation which is equal to v naught, and this is equal to the expression on e to the power is equal to ft upon mv naught. So it is of the form ft upon mv naught. So hence we can say that we have attained this expression: v is equal to v naught 1 minus e to the power minus ft upon mv naught. For this particular problem we have attained this equation. So let us deal with the problem. It is stating figure given below shows a square frame of wire having a total resistance small r placed coplanarly with a long straight wire. The wire carries a current I given by I equals I naught sine omega t. Find the flux of the magnetic field through the square frame, the EMF induced in the frame, and the heat developed in the frame in the time interval 0 to 20 pi by omega. So if we consider this particular problem, we begin it this way. Let us first of all understand it in this way, that this is the infinitely large current carrying wire carrying a current I, and at a distance b from it, the first edge of the square frame is there of side A. At a distance r, we are selecting a small patch of thickness dr. So we are selecting a small patch over here of thickness dr. So the area of this patch can be written as dA, which is equal to a dr. Now magnetic field due to current carrying wire can be written as mu naught I upon 2 pi r. So the value of flux associated with this small patch or small area is equal to mu naught I upon 2 pi r a dr, and now we are integrating both sides. So while we are integrating both sides, the limit of integration is from b to a plus b. So the net flux which we obtain over here, phi net, can be written as mu naught. The value of I is written as I naught sine omega t a upon 2 pi. Now integration of 1 by r dr is equal to ln r. So we will get ln of a plus b by b. So this is the expression which we attain for the flux through this square loop. So now the question is asking us EMF induced. So the value of EMF induced can be written as the magnitude of EMF induced is equal to d phi by dt's magnitude. So if we differentiate this expression with respect to time, we will attain the value of EMF induced EI as now mu naught I naught a 2 pi and the term in ln are all constant. The derivative of sine omega t can be written as cos omega t into omega. So the expression is written as mu naught I naught omega a upon 2 pi cos omega t ln of a plus b by b. So this is going to be the expression for EMF induced in the frame. Now in the last part, the question is asking heat developed in the frame in the time interval 0 to 20 pi by omega. So the first thing to solve for the heat is necessary that we calculate the value of current that is flowing in this square frame. So current is equal to E induced upon resistance, which is equal to small r. So the current which is going to flow in this square frame is equal to mu naught I naught omega a upon 2 pi small r cos omega t ln of a plus b by b. Now for the expression of heat energy, so we are writing du is equal to I square r dt, and we integrate this expression for the given time, that is from 0 to 20 pi by omega. Since the current is a function of time, we will be using this integral to calculate the value. So the value of heat energy will be coming out as, so all this expression of I square r. So if we make I square, so the expression will be mu naught square I square omega square a square upon 4 pi square r square ln of a plus b by b square, and we are left with the integration of cos square omega t dt from 0 to 20 pi by omega. So on solving this equation, we attain a value equal to, so the value of heat energy developed in this circuit is written as 5 times of mu naught square a square I naught square omega upon 2 pi r ln square a plus b by b. So this is going to be the expression which we attain on integrating cos square omega t from 0 to 20 pi by omega.